Hello everyone, and today we will continue discussing this Laplace transform and solving some examples using the basic definition of Laplace transform besides the properties we discussed earlier in part 1. So let's start. So first, let's return back to the definition. So we have this Laplace transform of any function in time domain or in domain t. This will be another function, which is big F in domain S, the function of S. It's nothing but the integration from 0 to infinity, e power minus st, multiplied by this function f of t, and the integration over t. And this is the definition. So using this definition, we tried to get some interesting properties. And then these properties, first, we have this kind of linearity, which if we have any function f of t and another function g of t, and we multiplied both of them with some constant, some scalars, and we have some addition or subtraction between them. So their Laplace transform will be the same as scalars multiplied by the individual Laplace transform of each of these functions. So we have the same thing here. And then we have also one of the interesting properties, which is the transformation if we have this function multiplied by exponential. So if we have exponential e power at multiplied by this f of t, which is the shifting properties, which means I will get this f of s according to the function f of t, and then this exponential will do nothing but shifting the s to be s minus a. And then we went through what happened if we just multiply it by t. So the multiplication by t, it's just the derivative in the s domain, and don't forget this minus sign. If you multiply twice, it will be the second derivative with minus sign twice, which means it will be positive. And we discussed this in the previous video. If we have, instead of this multiplication by t, we will have what happens if we have this division by t. It will be the opposite operation, which integration of this f of s with respect to the s and the limits from s to infinity. Number 5, what happens if we have the derivative itself? If we are deriving this f of t with respect to t, so this will end up in the other type in the s domain is s f of s minus f of 0. What's this f of 0 again? This is f of t, not f of s, at the time or at t equal to 0. The last one we discussed, it was the integration instead of this derivative. If we integrating from 0 to t, this f of t, let's call it here tau, for example, and then this will end up as just the Laplace transform of the integral function, which is f tau or f of t, and this integration will be transferred as divided by s. We can see here these functions or these properties can be summarized into some interesting property, like there is some kind of duality here. Here, from 3 to 4, if we just getting this out, and if we just discussing first number 3 and also number 5, you will see if we have multiplication here, this multiplication will transfer on the other side to be the derivative. And if we have derivative, which is number 5, it will end up on the other side in S domain to be multiplication by S. Also, number 4 and number 6, it's nothing, but if we have division on one side, on the other side, it will be the integral. So combining both together, you will end up with some recap for what happened for these 3, 4, 5, and 6 properties. Just if we have multiplication by t, it will be derivative in S. If we have multiplication in the S domain, it will be the derivative of t domain. If we have division if you are dividing by t, it will be integral in S domain. If we have integral in t, it will be division in S domain. So this is what can be called, basically, there is some duality in these properties. Besides this one, don't forget we have a small table for basic functions. We have f of t and the corresponding f of s, and we have this k, corresponding k over s. If we have t, 1 over s squared. If we have exponential, we have 1 over s minus a. And if we have sine or cosine, the denominator, as we discussed earlier, it will be the same as squared plus a squared, but the only difference is just in case of sine, it will be the constant. In case of cosine, it will be s. The same will be for the hyperbolic sine, which sine, and the hyperbolic cosine, which cosine. It will be the same as sine and cosine, but instead of this positive sign here, it will be a minus sign. So it will be s squared minus a squared, and the same numerator with no change at all. So this is just if we need to memorize this one. So after moving through this whole the definition and quickly on these properties, let's move forward on how to solve these examples later. So let's see if we are required to find some Laplace transform. So I need to find Laplace transform of the following functions. Let's start with one function, very easy, f of t equal e power minus 2t plus 7. So here, if we are trying to think about this one, the exponential, if we have a plus b, it will be nothing but e power a multiplied e power b. If we have this minus, it will be this one minus. So it doesn't matter if it's plus or minus. The exponential with some addition or subtraction for these powers, it will be exponential multiplied by each other. So that means this f of t can be rewritten as e power minus 2t multiplied by e power 7. What's this e power 7? It's a constant, so it doesn't matter. This e power 7 will be common outside this integration. And then we'll end up with the exponential. We need to find this Laplace transform too. So e power 7, and this exponential from the table, it's 1 over s minus minus 2, which is at the end 1 over s plus 2. And that's it. So again, very quickly, we have this function here, e power minus t plus 7. This function, it's nothing but e power minus 2t multiplied by e power 7. And then this e power 7 is a scalar multiplication constant, so just outside. And then we will end up with this e power minus 2t. From the table, it will be 1 over s plus 2. So let's keep going. If we have another example, function f of t equal e power minus t sine 3t. In this case, we have both of them from the table. So this is from the table, it's 3 over s squared plus 9. This is from the table 1 over s plus 1. But if we have multiplication together, we don't know. So what will happen? Just we'll get the benefit from the shifting properties, which means if I have some exponential e power minus t multiplied by any function, from the properties we discussed earlier, this will be f of s, and each s will be s minus minus 1, which means it will be s plus 1. So first, we'll get Laplace of the sine, which is from the table, don't forget. So it's just 3 over s squared plus 9. and this 9, it was nothing but 3 squared. What happened if we just multiplying this by exponential? What happened here? It means function this fs of this one make each s s plus 1, which will be here translated to be s plus 1 squared plus 9. If we're just trying to simplify this fraction, it will be s over s squared plus 2s plus 1 plus 9, it means plus 10. And here we got this value for this Laplace transform. So just we got use here of this shifting property. Just to remember. Okay. So what happened if we have another example? F of t will be equal t squared e power 2t. Again, as we discussed in the previous example, we have this exponential multiplied by sine, and we did the shift for sine. Here we have t squared and the exponential. Again, each one of them has its own property. So we have, if we multiply it by this exponential, it will do shifting. If you multiply it by t or t power n in general, which this n is a positive integer, it will do the derivative. In this case, this is the second derivative. So just thinking about this one, I think we are motivated more towards to do the shifting, which is much easier. So what this means? It means if we have two different properties and we need to choose one to start with, we start with the easiest one. So instead of doing derivative for a function, I can do the shifting, which is just adding or subtraction some constant from the s. So this implies that I will start with t squared, which is from the table t power n, it will be this n factorial, over s power n plus 1, which is s power 3, which is here 2 factorial, it's nothing but 2 over s cubed. And then what happened if we have this t squared multiplied by the exponential? Again, to remember, it means each s will be s minus 2. From where? From this one. So it means here this one will be 2 over s minus 2, and all these are cubed. And then we are done with the Laplace transform of this function. Let's keep going. Let's see another function, f of t equal t plus e power minus t all squared. So something like this, again, we don't know what happens if we have this bracket square or cubed or to the power of any integer. The easiest way, just to simplify this function to get this bracket resolved. So this will be t squared plus 2t e power minus t plus e power minus 2t. Each one of them, for solving, let's check. This one, it's very easy. This is the table. This one, it's from the table. And this one, as just we discussed, we can get t from table. And then this exponential will do the shift for the s function. So let's write this down. So Laplace of this function f of t, which is our required f of s, will be equal t squared, the first one, it's 2 factorial over s 2 plus 1, which is cubed, plus 2, and then this t, it's 1 over s squared, and then we have the shift, and the shift here, it means this s will be s plus 1. And the last one, it's again very direct from the table, which is 1 over s plus 2. So finally, this f of s, it's 2 over s cubed plus 2 over s plus 1 squared plus 1 over s plus 2. And here is Laplace transform of the given function. So again, to recap this very quickly, we have this bracket squared. We got the square out, so it will be t squared, the first squared, the first multiplied by the second multiplied by 2, and the second squared. And then from each of these terms, we can decide if we are using directly from the table to get this Laplace transform, or just have some application for this for the Laplace transform properties. So the first and the last, it's directly from the table, and the second one, it's just applying the shifting property after getting the Laplace of t from the table. So we'll end up with this one, which is very straightforward, and then we can move to a new example. So let's see a new example here. F of t, it's equal t plus 1 all cubed. Some of you for sure, you will have the value of this cubic bracket, but for those who are not aware of this one or can't memorize this very quickly, you can do it in much simpler way. So just this is, it's t plus 1 multiplied by t plus 1 squared. We did nothing. So just simplification. So this t plus 1, and then this t squared plus 2t plus 1. And then we can do this multiplication between both brackets. So it will give you t cubed and 3t squared and 3t and plus 1. So what's this one? This is our new function f of t. So if you just take a quick look on this one, all these terms, that's directly from the table. So here, f of s, which Laplace transform of this function, can be written as the first term is 3 factorial over s power 4, which is 3 plus 1, 3 t squared be 2 factorial over s2 plus 1, which is for 3, 3t, which 1 over s squared, and 1, just 1 over s. So then f of s finally can be simplified as 3 factorial, which is 6 over s power 4, and then once 3 multiplied by 2 factorial, which is 2, it will be 6 again over s cubed, and this s squared, and the last term 1 over s. And this is Laplace transform of the function here, which is t plus 1 all cubed. Okay, let's see a new example here. If we have this function f of t equals 10 cosine t minus pi over 6. So if we memorize the table very well, we will see that if we have any cosine, any scalar multiplied by t, we'll have this Laplace transform of s over s squared plus this a squared. But if we have this t plus or minus anything, we can do this in this direct form. So what will happen? We need to deal with this trigonometric function in a better way. So just to return back to some of these properties, we know if we have cosine a plus b or a minus b, this form can be rewritten as another form of cosine a cosine b minus sine a sine b. And if it was cosine a minus, it will be this one plus. So this is some like reformulate this cosine t minus pi over 6. So let's do it here. F of t will be equal 10. We'll end up with cosine t cosine pi over 6. And this minus will be here plus sine t sine pi over 6. Again, we need to get this constant, which is cosine pi over 6 and sine pi over 6, which is in radian. In degrees, it's 30 degrees. So sine pi over 6 and cosine pi over 6. This one is half, and this one root 3 over 2. If you don't remember, just use your calculator. You can get very quickly. So substitute with these values. So f of t can be rewritten with the new format, cosine t multiplied by root 3 over 2 plus sine t multiplied by half, and all these multiplied by 10 outside. So right now it's nothing but like transformation from the table. So this one, since the scalar constant is still common outside, and this cosine t, it will be s over s squared plus 1. And don't forget there is some scalar constant here. And this sine, it's nothing but 1 over s squared plus 1. And this scalar constant is still here. So just to simplify this new line, so this one will be 5 root 3, this s over s squared plus 1. And the other one will be 5 divided by s squared plus 1. We just need more simplification, which is not mandatory. We can write this as 5 root 3s plus 1 over s squared plus 1. This is root 3. And here, Laplace transform of this function, which is called cosine t minus pi over 6. This will open the door to get familiar with some transformation happened before in the trigonometric function. Just revisit these very quickly. So let's remember together. If we have sine A, cosine B, or if we have cosine A, cosine B, and if we have sine A, sine B, all these formulas, we can't use Laplace transform directly. And also some another formulas, very special cases, if we have cosine square or if we have sine square. So this one, if we have cosine A, cosine B, this was half sine A plus B plus sine A minus B. Both are cosines, it will be half cosine A plus B plus cosine A minus B. And if we have both signs, it will be half cosine the difference minus cosine the sum. If we have cosine squares, this is nothing but half 1 plus cosine of the angle. And if we have sine squared, it's nothing but half, instead of this 1 plus 1 minus cosine double the angle. If we can consider this transformation, you will end up with these cosine and sines and some constant, and all these terms just direct transformation from the table. So this is also, just remember something very quickly. If you have sine minus A, it's minus. This one is minus sine A, and if you have cosine of minus angle, this is cosine the positive angle. So knowing this, Let's see how to apply these in examples. So the new example here, example number 7, it's required to find Laplace transform of the given function f of t equal sine 3t cosine 2t. Again, we don't have any properties for this multiplication in the trigonometric function, but we have their own already properties. So this f of t can be rewritten as sine and multiplied by cosine. It's half sine the sum plus sine the difference, which both of them are in the table. So f of s can be rewritten, can be derived as this half is a constant. This sine, it's this constant over s squared plus this constant square. And this sine t, the constant here is 1, so it will be over s squared plus 1 squared. And here we have this Laplace transform. If we consider another example, visiting these properties, what happens if we have the same angle, sine 3t cosine 3t? So this will be much easier if we remember this correctly. This is nothing but half sine double the angle, so which is 60. If we have this, so f of s in one step, direct transformation from the table, it will be half. This one, 6 over s squared plus 6 squared, which is 36. So this will end up with 3 over s squared plus 36. And here also this is the Laplace transform of this example. Hey, let's see this new example here, f of t equal e minus 3t. So let's go with this new example here, this f of t equal e power minus 3t multiplied by t multiplied by sine 5t. For sure we know that sine has no properties at all, so it's something can be obtained from the table, from the direct transformation from t to s. T for sure has a property which can do the derivative in the s domain. And the exponential also has another interesting property, which shifting in the s domain. The choice right now, it's between using the derivative first or the shifting first. If we will use the derivative anyway, so it will be much easier and more like much simpler to use the derivative at the beginning while the function is still compact or has no more brackets with this transformation and shifting. So it's preferable to keep this shifting to be your last step. So I will keep this shifting to be my last step right now in this transformation. So what we'll be doing at the beginning, we'll do this sine 5t transformation, which you already knows from the table, which is 5 over s squared plus 5 squared, which is 25. And then I can do this transformation multiplied by t, which will do the derivative. So it will be d by ds for the s domain of this function sine, which is already obtained in the previous step. And we have minus sign, don't forget this minus. So right now, Laplace of t sine 5t will be, so here right now, we can get this derivative as s squared plus 25 all squared. And then we have here this minus sign, and we have this 5, and there's another 2s with another negative sign here. So this will be 10s over s squared plus 25. Sorry, same confusion here. So plus 25 all squared. So after this step, we have this final step, which like multiplication by exponential by this whole function, which already has its own Laplace transform. So this will make each s will be s plus 3. So return back here. So this will be 10 s plus 3. And then we have s squared. It will be s plus 3 whole squared plus 25. And all this bracket is squared. And then this is our solution. So let's move quickly here. We have this exponential, we have t, we have sine, one of them already in the table with no properties. And we have both of them, t and exponential, has their own properties, which one will do the derivatives, the other one will do the shifting. And we agreed on keep this shifting to be the last step. So we got this sign from the table, then multiplication by t will do this derivative here, and this is the simplified version after the derivative has been performed. And then multiplying by this exponential, making this each one of these s to be s plus 3, which is from this power of this exponent. So let's move forward to another example here. We have this f of t. Let's equal integration from 0 to t, e power minus 3u minus e power minus u divided by u du. So regarding this one right now, it seems we have this integration. So the integration from the properties of Laplace transform will be transferred into division. Yes, that's correct. Division by s. So the first step, how to get Laplace transform of these terms first. So I need to get Laplace transform. The first step, e power minus 3u, which is t. Doesn't matter the name of the variable, it's still in our t domain. So e power minus t minus e power minus t. Both of them are the table quantities, so s plus 3, and the other one here minus 1 over s plus 1. What happens if we have this term here divided by t? Yes, that's correct. I will do this integration with respect to s. I have this u plus 3 and this 1 over u plus 1 du. It's the same u or s, but again you will substitute with this s at the end. So here, this term will be this ln u plus 3 and ln u plus 1. And then the limits, it's from s to infinity. Sorry. So one of the things that will make this solution very simple and straightforward, if we have any ln, like these ones, ln A minus ln B, or if we have this ln A plus ln B, this can be simplified as ln A divided by B, and this also can be simplified by the product ln AB. And we have for sure, if we have n ln A, it's nothing but ln A power n. And also we have the value of ln 1 equal to 0. Just remember these things. So here, what's the benefits of having these formulas revisited right now? We need from these formulas, instead of substitution directly for this first ln minus the second ln, just try to make it only just one logarithmic function. This will be easier in the substitution. So this one will be, so Laplace of this function divided by t, it will be this ln u plus 3 over u plus 1, and we have substitution from s to infinity. We are using this infinity, so infinity, it means like you need to substitute with this infinity, this term, then u plus 3, u plus 1, minus, instead of each u, make it s, so s plus 3, s plus 1. The first term, which is this one, you can use L'Hopital. rule, I need to get derivative for the first part and the derivative for the second part. So this derivative will give you 1 inside the len, which will end up with len 1, which is equal to 0. So this one with substitution will give us 0. And then return back to our example here. So this division by t will be minus len s plus 3 over s plus 1. This minus sign again will go to inside this len, and I will get the reciprocal of this fraction, so len s plus 1 and then s plus 3. This is not everything. Remember, we have this term here, which is the integration. So here's the last step. If we are doing this integration for this whole function, so it means Laplace transform, it will be the same Laplace transform for the integrand function, and then just this integration will be transferred as division by s. And this is our result for the whole example here. So this Laplace transform. So let's again see what's happening here. We started with this exponential subtracted from each other, and then they have some division by t, and then last step was the integration. We don't have any kind of a choice for selecting this order of these properties, so the last step for sure, it's here in this case, it's the integration itself. So we did this exponential form from the table, which is 1 over s plus 3 minus 1 over s plus 1, and this exponential, and then after dividing by t or u, it's the same, it will do this integral from s to infinity. We did this integral would give us len and len, and we tried to make sure that we need to get this len functions into just one len by simplification of these using the len properties and logarithmic properties. So we'll end up with this len s plus 3 divided by s plus 1, and we have minus sign outside. So this minus again from the logarithmic properties, it will do this reciprocal for this fraction. So we ended up with len s plus 1 over s plus 3. If we know the whole bracket here inside the integration, we know the Laplace transform of this bracket. So the integration from 0 to t, it will do nothing but dividing by s. And this is what happens here. So hopefully this is clear right now. And then let's move to a new thing. So also beside using the Laplace transform to find these function in S domain, we can use some of these properties to evaluate integrals. So one of the benefits of the Laplace transform, we can use it to evaluate some integrals. With what kind of integrals at the beginning? For sure, if we have integral from 0 to infinity, this is the definition actually of Laplace transform. We have f of s from the Laplace transform definition. It's integration from 0 to infinity, and we have e power minus st multiplied by a function in t dt. So it means if you know this function f of t, and this function is multiplied by another function, which is exponential, and you need to get the integral of this one from 0 to infinity. So what will happen? All this value, it's Laplace of this function, and your s here will be the new variable. But taking into consideration what happens if it's not s, like we can put any other variable name, we can name it anything if it's alpha. So it means put s at the end to be alpha. So here, if we need to get this integral, so the integral value will be our f of s, but making each s equal to alpha. A quick thing, let's assume we need to get the integral of something very special. Like if I need to get 0 to infinity e power minus 2t t dt. It's it's an integration. Yes, it's an integration, but it's a very close to already the properties we know from the definition of Laplace transform. This is from 0 to infinity e power minus st t dt, but s here it's equal to 2. What this means? It means we need to get Laplace. Yes, that's correct, just for t, which is 1 over s squared. But don't forget, each s here is equal to 2, so the final value of this one, it will be 1 over 2 squared, which 1 over 4. So it means this integral will be equal 1 over 4 without doing a real integration, just using the definition and the properties of Laplace transform. So again, if we have integration here from 0 and this integration from 0 to infinity, and we have function multiplied by exponential, it will be Laplace transform of this function with the value here of s equal to what here in the exponential multiplied by t. So one quick question, what happens if we don't have this exponential? Like if we have just f of t dt, it means it's still a Laplace transform? Yes, it means it's still a Laplace transform, but with the case in this integration right now, it's Laplace of f of t, but right now s equal to 0, which here e power 0t is equal to 1. So a special case, it's this case right here. Taking this into consideration, we can move forward to apply these integral values. So what happens if I need to get evaluation? Like let's see here, evaluate the integral. And I have the first integral right now. It's I equal integration from 0 to infinity e power minus t sine 3t dt. Again, we have function multiplied by exponential, and we have the integration from 0 to infinity. If we have the three things, so this means this integration, it's nothing but Laplace transform of this function, but consider this as is equal to 1. Again, we are comparing this with e power minus st f of t dt, and the integration from 0 to infinity. So here, I will do this Laplace transform. It's from the table, very straightforward. It's 3 for s squared plus 3. Don't forget, is equal to 1. So this will be s3, over 1 plus 3. So this integration will be for 3 squared. Sorry for that. And then this equal right now 9. So this is 3 over 10. This is our integral value. So again, this is exponential multiplied by sine, the integration from 0 to infinity. So Laplace of this one will be the Laplace transform of this sine with substitution of this s equal to 1, as we can see here from this exponential. So this will be 3 over s squared plus 3 squared, which is 9. Substitute as equal to 1, this will end up with 3 over 10. So let's see another example here. We need to evaluate the integral. I equal integration from 0 to infinity e power minus 3t minus e power minus t, all divided by t dt. So from the beginning, don't get confused. We don't have exponential. This is our function. Like this is our f of t. and we don't have the exponential e power minus st here, which means it's equal to 1, which can be simplified as our s here, it's equal to 0. So this integral will be, as we can see from this definition, it's Laplace of the whole function e power minus 3t e power minus t divided by t, putting s equal to 0 at the end. So if we can get this one done, again, we did this previously in the last example in our Laplace transform properties 2 slides before. So this was ln s plus 1 over s plus 3. And then right now we need to substitute s equal to 0. So this will be ln 1 over 3. So getting this value here means this is the value of this integral. Again, to move quickly over this one, this was integration from s to infinity, 1 over s plus 3 minus 1 over s plus 1 ds. And we did this after substitution, we got this one. We did this more details. And we need to find the integral right now. So the value of this integral is ln 1 over 3. So again, this one is a number. Just quick question here. What's the Laplace transform of 0 to infinity e power minus 3t minus e power minus t divided by t dt? If you think about it, this one is constant. So Laplace transform of constant is the constant, is this constant divided by s. What's the value of this constant? It's ln 1 over 3. So this one will be divided over s. Again, here we are doing Laplace transform. Previously here, it's evaluation of integral, just trying to differentiate between both cases. So the value of the integral, it will be constant, as the integration limits it's from two constant from 0 to infinite. If I have the value of this integral, so its Laplace transform, it's nothing but its value here, but divided by s. And that's it. Hope it's very clear right now how to use the Laplace transform to find any transformation using the properties and the definition. Besides this, you can evaluate many integrals from 0 to infinity using the definition plus the properties as we discussed in these several cases. So thank you for listening and see you in the next one.